So can you start? Yeah. Okay, good. Okay, so yeah, let us recapitulate what we did. I mean, I'll use some shorthand notation for what we did. I mean, it's boring to write down all the integrals and so on and so forth. So last time we calculate this, and then schematically what we did is, this is the decay rate, and then we did we calculate this scattering amplitude squared. I mean decay amplitude squared, and then took sum average, phase space integration, and so forth. So this is a production of Lepton asymmetry. So producing by 1 unit and then minus 1 unit. And then we have inverse process, one Lepton number disappearing and one Lepton number appearing. Then we didn't consider any other processes, but here, and as a result of that, what we had is I don't write down this number. So there's a 3-level decay amplitude squared. And then so we do all the integrations and so on and so forth. So that wasn't a correct sign. So, okay, so this is the decay term. There is asymmetry in the decay. And then the inverse decay there is also symmetry inverse decay picking up. So this FLFH goes to FNEQ due to energy conservation. And then asymmetry, there is asymmetry in this inverse decay rate, also asymmetry between N and L bar, the number symmetry pick up this. So now, so you are considering the N decay and then N production, but the thing is that there is the process made by N. So this 2-2 scattering can have this unshelled contribution, right? So since this all the process was included in this case, so we have to also, I mean, okay, so this S channel, also there's a T channel diagram, but the T channel diagram is not relevant for this question, so we don't discuss that. So, okay, here, this 2-2 scattering, violating Lepton number by 2 units should be included. So there is so LH going to L by H, there is a minus 2 unit change. So there's a plus 2 unit change. And then this unshield contribution should be subtracted. So this is from and yeah. So I mean, so this there is an exchanging delta equal 2 processes. Also there is also delta equal 1 process involving 탑각육화와 gauge coupling and so on and so forth. So to be complete, I mean we have to include all of those, but let us not discuss all these contributions. They are usually gives a small correction in many cases. So now, so let us examine what you can have from this subtracted process. Okay, so this is actually LH2 L bar H bar minus so initial production, then so this initial contribution should be subtracted, right? So this is so we okay. So so this was one. This branching ratio has a small asymmetry, and then this is the same as n going to L bar H bar. So there is for this we have additional factor. So this whole quantity has some small deviation due to asymmetry. So, and then this is in terms of Yugawa coupling. This is order of y to the 4, and this is order of y squared, right? But there is a okay. So then this we say. So CP conserving part we group together, and then there remains CP violating part and CP asymmetric part. So this whole quantity we'll call the process and exchanging process with unshield subtraction having no CP asymmetry. Of course, if we go higher order of y, then so there is also kind of epsilon effect. But at this order, we just neglect that. So, okay, similarly, we can calculate this as well. I mean, it's not that gamma. I mean, after the whole integration, we get some quantity which we call gamma and so. So yeah, at this moment, let us say so. This is subtract. So this has no CP asymmetric. Has no CP asymmetry. Is the same, but we have negative sign for the CP asymmetric part. So you plug in that to here, then what you get? so you take this, you replace FL, FH by FNEQ, then you subtract these two, then you get epsilon contribution with -2 sign. And then, okay, and then the other part, CP symmetric part, you get difference between these two, the CP asymmetry. And following our previous notation, this is okay, adding these two, you get minus sign, correct. So in this way, I mean, everything becomes now consistent. So considering all this, what you will get, so now I go to the notation in terms of Z. And then and of course, we have to include all the other scattering diagrams, which you can find in many references.
Scattering link asymmetry? With scattering link asymmetry?
Good question. Let me see.
Recently, some work was done saying that
Scattering, I mean, here, yeah, all included here. It's not only N, also N going to L, H, gauge boson, or top quark. So the gauge interaction and Yukawa interaction and so forth. So it's a delta equal 1 process, and that kind of thing all goes to the Tutu scattering, which I didn't.
So what is this
Gauge boson. Yeah. Vector field. I mean, typically this the scattering processes are smaller than decay and inverse decay. So.
But curious general question, can link asymmetry, that's the point you're making.
Yeah, at higher order probably. Yeah. But not at the leading order we are thinking of. And then again, so when I do the calculation, when I need repeat the calculation, I also neglect. So I just take this to see the behavior. So if you are not serious about getting exact result, so to see the rough behavior, and then you can solve this equation. So this is asymmetry generation. This is washout. It's a negative sign. So once, from this process you generate asymmetry, delta L, then plus delta L will be reduced if this contribution is large. So, so that's a general feature of this Boltzmann equation, and then usually what so yeah, actually last time we talked about it. So gamma D is this quantity. Gamma inverse D. So this inverse coming from inverse decay washout, and then we have remember this YNEQ or NNEQ is proportional to Z square K2, right? So we wrote it last time. So in the limit, now K was defined by gamma n over H1, so meaning at T equals M, and gamma n was decay rate. Then, so gamma D goes like a gamma n times Z1 for Z much smaller than 1. And low temperature, it goes 1. So at high temperature, this decay rate is, it goes like m squared over T. So higher temperature, decay is suppressed. And this goes to gamma n so high temperature is Boltzmann suppressed inverse decay. For this process we have to overcome at low temperature this Boltzmann suppression distribution. So it's obvious, right? To produce right-hand neutrino from NL inverse decay, there must be huge suppression. But the low temperature is suppressed by T, the same as decay. And then the intermediate region, should be order of gamma n. So from this, what you can see, so if we draw gamma D in terms of Z, gamma D goes like this, and it will saturate. And then gamma I inverse decay will follow the same as gamma D, and then at low temperature there will be Boltzmann suppression. Now, depending on K, if K is order 1, so this is Z equal to 1. What do you have? This is H. H scales like a Z T squared. 1 over Z squared, right? For K much larger than 1, this rate gamma n is large, so it goes like this H. So gamma d, gamma inverse d will be much larger than Hubble parameter. This is a Hubble parameter when k much larger than 1. So we have a period when gamma d and gamma d is larger than Hubble parameter. So this case. Yeah, in the radiation area. Yeah. Actually, actually it's confusing. So we know Hubble is like a t squared over 1 Planck, roughly. And then we introduce Z, and then whenever I introduce Z, I have to also rethink in terms of Z. So this is, Z minus 2. So this minus 2 slope. So for k is much smaller than 1, must be like this. So then from this you can guess. Okay, for k much smaller than 1, if you start with vanishing right-hand neutrino number density, initial number density, then this decay and inverse decay or scattering should produce right-hand neutrino abundance, and then it will decay at some point and produce asymmetry. So then the amount of asymmetry you can produce could be suppressed. So, in the beginning there was not enough number of right-hand neutrinos. Of course, this right-hand neutrino can be in thermal equilibrium due to G prime if you assume B minus L G prime interaction at high temperature. So initially, the number density of right-hand neutrino should be almost same as number density of a photon. So Y number of 10 to minus 3. Okay, this depends on the your initial assumption. And then for k of the 1, it's a kind of optimal case. So this inverse decay is close to can be summarized, and then decay produces symmetry. So here there would be no large Oshao effect. Y-axis is some rate. In some unit. Or if you like, you can draw gamma over h. So if you draw gamma over h, 1 is here, and then depending on k, you may have, it is k over 1, k larger than 1. So there is a period, gamma over h becomes larger than 1, corresponding this period. Okay, good. Okay, so from this behavior, actually, can parameterize the final lepton asymmetry like this. So this is initial abundance of right-hand neutrino. This is the CP asymmetric quantity of the decay, which is particle physics input, and kappa is called efficiency. So kappa becomes order 1 when k is order 1. Kappa goes like I mean, this is my approximation, so you shouldn't trust it too much. So different authors, I mean, there is a more precise calculation, so there may be a factor, some
Happens when K is much less than 1? What happens to kappa when K is much less than 1?
in that case, yeah, in that case, kappa small. Which I don't know how to write in terms of K.
So because when it is very small, K is very small, it's out of equilibrium, that is why the efficiency reduces.
That's right, yeah. I think story is different. If, I mean, as I said, you can just assume from the beginning it was in thermal equilibrium and decay. So K is more, in that case, actually, K is smaller than order 1 doesn't matter. Is that right? Yeah. Yes. So there is a plot showing this behavior in one of the references. Yeah, that's right. I think so. And then this is the case only when you assume there was no initial number density for right-hand neutrinos. So, I mean, in the scenario where right-hand neutrino is produced only by this decay, inverse decay, and scatterings, and it's kind of a freeze-in process. Okay, so then, so if you just include the leading contribution and solve the Boltzmann equation, what you will get? Is okay. I mean, these guys. So I take this plot from Bukumlo et al. Pedestrian paper. So for k 10 to minus 2, so they show there is a yn EQ plot. And then, assuming initial vanishing number density, this is yn, and then there is a symmetry. From produced yn, we will have a symmetry generation, and then it goes like this. So in there you need, okay, so assuming some arbitrary value of epsilon. And in there you need, this was around 10 to minus 10. And for k 100, this is equilibrium distribution. And then what we'll get is yeah. This is so evolution of yn, and then y delta L. I mean, it's immediately larger than that one, so it shoots. But and then coming back, I mean, there was no there's a plateau, meaning no asymmetry, no inverse decay effect. But here it shoots up, but then it decreases a bit. And then, so the final number they have is around 10 to minus 9. If k equal 1, then probably we'll have kind of this plot. For yn, y delta L, guess something like should be larger than 10 to minus 9, say, I don't know, 10 to minus 8 something. So no washout effect. So this is due to the inverse decay. Okay. Then from this, actually, you can see the behavior like this. So in this decomposition, yeah. So yeah, this kappa. Follows this kind of behavior. Okay, so questions? Let's run to the.
So the decay is creating the Lepton asymmetry, and the inverse decay is trying to wash it out.
That's right.
So how to think about this case, different case, case plus to one, case plus to plus to, how to think about this rules? So k is equal to minus 1. So does it
K equal to 10 to minus 2. Sorry, what was the question? Okay, K. Is this ratio. So decay rate, the usual decay rate in particle physics divided by Hubble parameter. Hubble parameter temperature dependent, so it's calculated at T equal to M. Mass of right neutrino. So K large means that the decay rate is larger than Hubble parameter at this temperature, and K much smaller than so right hand neutrino couples to Lepton and Higgs only through the Yukawa coupling Y. So this means that K small is Y small, so that all the scattering or the process is weak. And the K large is strong. So since it's strong, from the zero initial amount of right-hand neutrino, it can be produced. Right? So since coupling Y is large, so LH inverse decay will produce N, large amount. And at the same time, it can produce large asymmetry. But at the same time, the inverse decay also very strong. So inverse decay as it shoot up, but it will decrease. So this is the effect of the washout inverse decay. So okay. To get a better sense, just take the Boltzmann equation and just solve for it. It takes only.
So the washout effect is important when this curve
Washout important. Yeah. Okay. So this I showed the. Okay. Good. Gamma over H goes like this for inverse decay. So this inverse decay is in equilibrium. It's a process is larger than Hubble parameter during certain period. So then, okay, at lower temperature, the inverse decay is ineffective. So basically, this happens until this temperature, basically. For k equal 1, so it's barely in equilibrium. So for k equal 1, we wouldn't have this kind of view. You would have just this. If produced, just stays. Okay, so it's reasonable, right? Okay, now L asymmetry produced from the right-hand Newton decay. So you got interaction, say, now let us try to calculate this quantity. Okay, so let's take the right-hand neutrino. And for this, we need to consider all the three copies of right-hand neutrinos, or at least two we need, which will be obvious. And then let's consider producing alpha flavor of lepton. Then N1 decay produce L alpha and H. So this coupling is what? Y alpha 1. So having only this three-level diagram, if you square it, there is no symmetry. So symmetry appears next order in Y, adding this one-loop diagram. So same final state, L alpha produced and Higgs produced. And then, okay, so if you remember the direction of the arrow, here we have coupling. So if N comes in, L and H going out. So L going out, N come in, H going out, and here H going out, should also L go out from the vortex, and then N should come in. So, I mean, of course, this is a schematic way of understanding the. I mean, if you do the amplitude calculation, you will see this diagram will pick up the mass term in the propagator. So then here, L comes in, N should come out, and H also come in. But this doesn't match with this. So initial state should be N1. Then this means that if you do the calculation, so the amplitude is to pick up M1. So you sum up all the gamma matrices and then take a trace. Then, okay, so you will get this result. Two mass insertions. To match. I mean, it has no mass insertion. So one mass insertion will flip. Yeah. And then, yeah, asymmetry, of course, you take bar contribution. So, okay, and then there is also, this is a vortex diagram, there is a self-interaction diagram. Okay, so this is, let's say, this is 1, okay, this is beta, it can be different from alpha, beta 1, and then, I mean, this is alpha 1, then this is beta 1 star. This complex conjugation of this vortex. And this must be beta j. This is alpha j. So if you have only one flavor M1, you get let's take it later. Again, in the same way, we'll get so the coupling structure should be the same as the vortex diagram. Okay, so it's an exercise for you to do the whole calculation and then calculate this okay, for n decay to L alpha h, the rate should be proportional to one loop integration for vortex, correct vortex and self interaction, self energy diagram. And then for n going to L bar, H bar, we should have complex conjugation of this, right? But this one loop integration is the same, must be same as before, right? Or imaginary of this one loop integration.
So all of these things have been very high energies.
Yeah, around temperature, say M, 10 to 10.
Yes, yes. Is the running of these Yukawas important? Is the running of these Yukawas?
Good question. Yes, in principle, but we don't care.
So if you are assuming that between the values at high scale,
Yeah.
we are not.
Yeah. So yeah, we running effect must be small enough, I guess, or not.
No. Depends on the texture.
Depends on
On what you choose.
texture.
The texture.
Yeah. For instance, degenerate case, running effect can be large.
Yeah.
Yeah. Yeah.
Inverse hierarchy. Typically, the neutrino running is very large, and so it will reflect in the Yukawa running also.
That's
But
right.
There is
Yeah.
one Yukawa which is very large, at least one Yukawa.
Yeah, hierarchical Yukawa. Yeah.
Yeah.
That's right.
One of the Yukawas is very large, which is as large as one Yukawa, and its running effects are large. So it reduces by 0.5% because it couples also with top one.
That's right. Yeah. I was forgetting about.
So with this kind of
Okay. Yeah.
years ago also,
Yeah, that's right.
20 years ago.
Yeah. Okay, in certain cases, yeah, it's important to include the running effect as well. Yeah.
But in general, these are all free parameters, so you have a lot more freedom.
But in the end, you also have to use this to get the neutron mass.
No, need not, because there is much more freedom in neutron mass, because this has a right-handed mixing also.
Yeah, in fact, you are right. I mean, the quantity quantity for neutral mass generation is different from the quantity appearing in the leptogenesis. I mean, it's a running effect.
So the phases
In principle, should be included.
only
But
in certain cases, maybe the phases in the original.
so in short, so if you have only one flavor of right-hand neutrino, no imaginary part. This you know, right? GKM structure. And then, in addition, we must have imaginary part from the loop integral itself. So indeed, this is interesting. So in fact, if you cut this diagram, if n decays to n, also in any direction, in this cut also n can decay to LH. So the thing is that if decaying particle mass is larger than the sum of the particle masses in the loop, then we get imaginary part. So IVS is some loop function times theta of plus real part. So only when m is larger than the masses in the loop, you get non-vanishing contribution. So it's your homework to do this one calculation and see this. Okay, so now epsilon. And then also, okay, including flavor effect, I mean, we just sum up all the flavors, alpha and beta. We summed up the flavor, okay, sigma, L alpha. But if there is a flavor effect at different temperatures, then we cannot sum up. So we have a more complicated expression. And then, okay, in this case, we only consider N1, assuming the lightest one giving dominant contribution. And then epsilon 1 is okay, and then, the neutral mass matrix is y nu M inverse Y naught transpose V squared. So, I mean, for some Y, neutrino equal coupling, so we have to generate right neutrino mass matrix, and then also you can generate CP symmetry and Lepton symmetry, and which will convert to baryon symmetry of the universe. So, I mean, this is your model parameter dependent part. So you put some equal coupling and the masses of right-hand neutrinos in your favored way, and then check whether, and then depending on K, the epsilon should be also determined properly to get the baryon number of 10 to minus 10. Okay, so here, I mean, one thing is that we need the imaginary part. So if you think of any other this kind of one-loop process generating a symmetry, so this condition should be met. Not only in this leptogenesis case. And so there must be CP phase. So non-vanishing imaginary part in this combination. So if I have only one generation again, so there is no CP symmetry generated. So you need at least two right-hand neutrino. And there could be resonance effect. I mean, if one of the right-hand mass is very close to the lightest one, then there could be huge enhancement. So typically, this leptogenesis works at higher mass, say 10 to 10 GeV. But you may like to think of this low scale type 1C, so then this may be TeV range. In that case, epsilon should be very small. So it can be smaller than 10 to minus 10, which you need for baryon symmetry. So then you can enhance this by going to this resonance point. Of course, there is a limit. So here, I mean, we forgot about, there's at the resonance, we should include in the propagator the decay term here. So there is, the limit for this, but you can go close to x equal to 1 and to enhance the CP symmetry quantity epsilon. So this is called the resonant leptogenesis. So and then there's one important observation made by Davis and Ibarra on the limit of epsilon parameter. So it's the rigorous proof. You can go to the original paper or some other references. So I wouldn't repeat this rigorous proof, but give you some qualitative argument. So epsilon goes like y3. Do I have 3 there? Okay. So it becomes when there's a hierarchy between M1 and 2, 3. So roughly this formula holds. Again, this bound doesn't apply to resonance case. No, I'm following in my note. Yeah, the kind of more rigorous calculation is written. Maybe something's wrong here, but anyway, so please try to drive it by yourself. So this whole quantity goes like
There should be a K somewhere. Or J or
sorry, in my note K is written. So this is a seesaw formula. I mean, okay, this part. And then next step. Man, okay, this is becomes rigorous. Okay, so far all the equations are just identities, and then at the final stage, so you are assuming hierarchical neutron mass, M nu 3, the heaviest, the largest. And then from this we get, taking the heaviest mass, we get this, yeah, I mean, basically this is quantity smaller than 1. So from this you can calculate I guess this must be 0.05 electron volt. So this is y delta L or y b should be around 10 to minus 10, and then we said this can be written in terms of these parameters. So y and eq, we just assume equilibrium distribution. N and EQ over entropy density, which is around 10 to minus 2 or 10 to minus 3. And then kappa, assuming the maximal efficiency. Then what we need for this quantity is 10 to minus 7. Here, so if M1 is smaller than, much smaller than 10 to 10 GeV, basically our epsilon parameter is cannot explain the Baryon symmetry. So M1 smaller means that neutrino quark coupling should be small again to get right neutrino mass. So roughly, I mean, this is qualitative argument. So M1 smaller, we need the smaller y so that, this epsilon is proportional to y squared. So denominator is y squared and then numerator is y to the fourth. So basically, epsilon goes like y squared. So
equilibrium takes here to take it to be 10 to minus 3. That's for the lightest.
Yeah.
The lightest, it can be even smaller, right?
No, it shouldn't. It's,
So if you take, that's good, then you won't get enough asymmetry.
뭐 zeta function I don't know. So take 100, maybe a bit larger than 10 to minus 3. Of course, assuming vanishing initial abundance, the bound will become more serious. So, I mean, yeah, this is a rough calculation, but if you do some more rigorous calculation, M1 shouldn't be smaller than 10 to 10. Assuming there is no resonance and neutral mass is hierarchical. So this is assumes that mu3 is larger than m2, mu2, mu1. This is okay. So this is assumption. And so we assume hierarchical mass. So the m3 squared will determine delta m squared atmospheric, which is about 2-3 times 10 to minus 3 eV squared. So that was why I took m3 0.05. Yeah, thank you for the question. Okay, so obviously, if we have a resonance effect, this whole calculation doesn't hold. But generally speaking, so we have this kind of behavior. So if you go to the low energy, low mass seesaw, then generating the right amount of CP asymmetric quantity becomes difficult, so that you have to rely on this resonance effect. So let's see, for TeV scale seesaw, so this factor, suppression factor becomes 10 to minus 7. So resonance effect, you need x was this one, it's close to 1. Must be 10 to minus 7. Then you can compensate the small quantity of epsilon. So actually it's a general feature of a seesaw mechanism that the low energy seesaw is really difficult to realize the proper leptogenesis. Okay, I think
So this assumes that the value of this kappa is approximately 1.
yeah.
So, but value of kappa can also be different, right? So in those cases,
I mean,
we have
it's really optimistic upper value. I mean, generic, okay, so maybe it's safer to take kappa 0.1. Now, of course, yeah, depending on the different situations. Yeah, I mean, this is assuming, very optimistic. So if M1 should be smaller than 10 to 10 GeV, that means if you think of some cosmology and inflation, reheat temperature of the universe should be also larger than 10 to 10 GeV to get this thermal leptogenesis scenario. So if you have some the cosmological scenario predicting some reheat temperature, then okay, you may consider this kind of a bound as well. So this is famous Davis-Nibar bound. I think that's all I have to say. Then time is almost perfect. Okay, so questions?
So here we assume that only the lightest brightness and neutrino contributes to the CPS.
Yeah.
And all of the higher
Yeah,
brightness
yeah,
are being washed.
yeah. I mean, they are heavier. I mean, so in particular in this scenario, so M23 must be larger than, I don't know, 5 times.
So they will also at higher scales impose some asymmetries, but those are washed out by the lower.
That's right. Yeah, typically that's the case. Yeah. And then, of course, there are also cases whether you have to also take I don't know, I never thought of that seriously, but yeah, there are some cases you have to consider this N2 leptogenesis seriously. Or in the degenerate case, maybe 3 of them may contribute. Yeah. Is that right? Yeah.
Can you say again what you were talking about is reheating temperature and how this connects to this?
I mean, if reheat temperature is, say, 10 to 8 GeV, then there is no right-hand neutrino in your soup. So, I mean, we are assuming radiation domination era for this thermal leptogenesis. And the automatic meaning that the temperature at that time must be larger than the mass of right-hand neutrinos. Yeah.
So reheating temperature cannot be lesser than
The right-hand neutrino mass, yeah. Otherwise, the thermal leptogenesis doesn't work. It may work. Reheat temperature is 2 times smaller than 10 to 10 GeV, say, then if you have a large K, still decay, inverse decay and equal. So, yeah, there is, but generally speaking. Yeah. Okay. So thank you for listening. And then also, I mean, I will be here until the end of this week, so you can come to any time whenever I am there, so to ask questions concerning leptogenesis, baryogenesis, or whatever. Okay, thank you very much.
Thank you.